Hello gang, welcome to Kerbal Space Program. This is a little game that I play, and it's actually just got a really great physics engine. It is designed to simulate space exploration, so I'm going to use this and this little world here to try and show you a bit about orbital mechanics. So first we're going into the tracking station so that you can get a layout of the land, as it were. So this is the Earth analog called Kerbin, and I'm going to pull up the information on it. You might not be able to read that, so I'll read it for you here. It has an equatorial axis of only 600 kilometers, so it's basically 1/10 the size of Earth. They've played around with a few things. The mass is 5.29 times 10 to the 22nd kilograms. It's got an average sea level gravity of 1 g, so that's pretty normal. The escape velocity is 3,431 meters per second. I might talk about that later. It rotates only in 6 hours, so the day on this hypothetical planet would be 6 hours long. And then there's this thing called the sphere of influence. Basically, once you get out beyond that, gravity is so small it doesn't exist. In the game, they just chop it right off, make calculations easier. And then some other characteristics about it. The atmospheric height, they say for the game that here the atmosphere only goes up to 70 kilometers, and again they just chop it off after that. In reality, there's no real end to Earth's atmosphere. It just sort of slowly peters out. We have one atmosphere down on the surface, and the average sea level temperature 287 K. All right, let's zoom out a little bit, just so you can see more of the system here. It's a little bit different. There are two satellites here. There's the Mun, and then there's Minimus. They just decided to throw that in for a little more fun and exploration. Zooming out, we can see some asteroids that my tracking station has picked up. And zooming out, we can see the whole solar system that we've got. So there's a whole bunch of analogs. Mercury analog, Venus analog, there's Kerbin the Earth analog, Mars analog. Instead of an asteroid belt, we have just one planet dress. And then we zoom out a little bit more, and there we go. We can see Joule, which is the Jupiter analog. And then last but not least, Ilu, which is kind of sort of an amalgam of Saturn and a whole bunch of different things. But we're going to go right back to Kerbin, because really I just want to show you some basics of getting up into a simple orbit and then a geosynchronous orbit. So we're going to head over into the vehicle assembly building. All right, and then here is just the simple satellite that I have ready to go. It's got a main engine, a couple of boosters. They're solid fuel booster rockets. And then, so this whole thing here, from everything that's lit up, that's just to get that top part up into orbit. So I'm zooming in for you here, and you can see under the airfoil there's the actual satellite that will be in space on its own way later on. So I'm going to pull out the engineer's report. I don't know if you can read that. The mass is 17 tons. That's that number right there. I'm going to pull away everything that is just to get my satellite into space and then reread the mass. And just that bit right there, that's the satellite. Now the mass is down to less than 1.5 tons. So think about that for a second. 17 tons. 15.5 of those tons are just to get 1.5 tons up into space. So just to give you an idea of how hard it is to get up into space. All right, so now we are trying to launch. Now we're on the launch platform here. I've got an add-on here called Mechanical Jeb, Mech Jeb, that helps, in this case it's going to be my autopilot. There's the calculations that it's done for me. I'm going to turn on the ascent guidance. Go ahead and turn on the piloting systems, thrusters up, hit the guidance nav ball, and then we're going to get up to an orbit of 100 cam. For you, that's worth you knowing, and off we go. So you can see pretty quickly that what's going on is that we are rotating and we're already beginning to angle our thrust a little bit. You don't just launch straight up into space. You can see that the speed there, obviously we're going faster and faster as we go because we're accelerating up. Alright, so we're just about at the first separation, going just shy of 400 meters a second. Separate the solids, they're used up, get rid of them, turn the main back on to nearly full, and punch through the rest of the atmosphere. So you can see that that's the little slider up above that's showing you the atmosphere is dropping away as we get higher. And then if you can read that, that's the apoapsis, and that means the highest point on the orbit, or in this case it's not yet in orbit yet. And so we want to get that up to 100 km. You can see we're going so fast right now that we're actually pushing against the air particles so that they're causing friction to the ship. So that's why the ship would be heating up. Alright, so the thrusters just cut out because right now we're on a trajectory to get up to 100 km. So this means with nothing else happening, we'll get as high as 100 km. I've pulled out to the map so I can show you. Here's the real cyan line there. That's the trajectory that my craft is on. This is called a suborbital flight. You get high enough to be in orbit, but it's not an actual orbit. So if we did nothing else, we would get up into space and then fall right back down to the surface. The first two of the Mercury program flights did just this. So now what's happening is the computer has plotted out for me the orbital burn. So when we get up to that highest point, what's going to happen is the thrusters will turn back on. There we go, we're back at the craft. There go the thrusters. You can see the speed is increasing. And now what we're doing is we're going to be pushing our spacecraft fast enough sideways so that now it's going to achieve an actual orbit. And we're nearly there. So if I click out on the map and then I zoom around a little bit, you can see there's that light blue line there that shows us the orbit, and we have achieved basically a circular orbit, just a hair off. You can see the apoapsis is just a bit more than 100 kilometers, and then the opposite of the apoapsis is the periapsis, and that is just a hair left, 99.7 km. So very nearly circular, not quite. So a couple of things to be keeping in mind is that, remember, this is not exactly the same as our system. So our little 100 km orbit is a bit low. The space station's about 200 up, and then the planet is actually about a tenth the size that Earth really is. So it's not quite perfect, but it's a very good analog, good enough to show you what's going on. Okay, so now let's go ahead and let's get ourselves out to the geosynchronous orbit. I'm pulling up my little autopilot again, and this time what I'm going to do is I'm going to change the apoapsis. I'm going to tell it to say, I want you to go out and make a much larger orbit. And what we need here is 2,864 km, so I'll type that in. Alright, I'm going to tell it to create the burn, and then that yellow dotted line is what the orbit will be after I do the burn. And you can see it's a very elliptical orbit, not at all circular. We're not going to get into the math of that at all, but you can see that it's going to take 651 what are called delta V's. So the delta V's, if you can see that there just above the little globe there, the delta V's are telling me how much fuel basically I need to burn. They're sort of the currency, if you will, of space travel. So it's just turned on the time warp for me. You can see it repositioned for me. Alright, so we've started our burn, and you can see we're going to use up this rocket, get rid of that, and then turn on the little baby rocket. So now this is finally the little tiny satellite that we were trying to get out into orbit. And this thing actually has a ton of leftover fuel, way more than I really needed. But I wanted to have it just in case I was just going to show you anything else. So once again, we're getting the burn nearly done. It's going to finalize. And there we go. So I zoom back out, and now that blue line there, that is the actual orbit that we'll be taking to get out to as far out as the geosynchronous orbit. And you can see that it's way different. Orbital mechanics get a little bit interesting when we get into oval stuff, but that's going to be a bit beyond what we do. Really quickly, though, the way that orbits work is if you were to find the area that sweeps out, so imagine drawing a triangle, boom, 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 okay? That area there would be swept out in the same amount of time as the similar area, but when you're way closer in. So if you think about that for a second, what that means is that when you're way closer in order to have the same area as when you're way out, you have to be going way faster. And that's exactly what's happening. Now, again, the math to this gets a little bit complicated, but if you just translate it back to the notion of potential energy and kinetic energy, think about falling, only obviously we're not hitting the ground here, but when you're way out there, you've got all this potential energy, but when you're in close like we are right now, and you can see we're going just under 3 kilometers a second. So we're really, really fast close in, and then when we get out to the apoapsis, then we go really, really fast. So right now I'm changing the periapsis, so I'm telling it that when we get all the way out to the edge, what I want you to do is make another burn, and then that will circularize again. So that's how you change your orbit, is you do an elliptical burn to get out, and then you do a circularization burn to stabilize your orbit. So I'm going to tell it to go ahead and get started. Okay, and now we are going to time warp on out. We're going to, as we get closer, it's going to align itself and get ready for the next burn. Get these out of your way so you can see a little bit. And so this next burn is going to cost us 424 delta Vs. We've got that, and plus plenty more to spare. So you can see what's happening is as we're going faster and faster, the orbit is becoming more and more circular at this point. And what's going to happen is the periapsis, that little tab you can see on the right, when they're getting closer to each other, is growing, 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 and then we're out to the right size. Now, if we'd kept burning, we would have turned into yet another elliptical orbit, but we didn't want that. We wanted to circularize. So now you can see that our orbital period is really, really close, 5 hours, 59 minutes, really close to the 6-hour day that Kerbin has. It's not exactly perfect, but pretty gosh darn close. And so then we can test this. I don't know if you guys can see Kerbin particularly well, but there's this little tiny green arrow right there that we just wound up, and that's more or less pointing. So I'm going to turn the time warp on. We're going to go really fast. Oh, shoot, too fast. Sorry. So let's turn that back off. And so let's look again. Unfortunately, it's in the dark side, so we're going to have to wait till we swing back around again. All right, so as dawn would be breaking over that peninsula, there it is again. And you can see that little arrow, just hard to see, but you can see it. It's pointing at our little simple satellite that's in our geosynchronous orbit. So we've done it. We have achieved an orbit that if you were standing on that peninsula looking up, you would always be able to find this little satellite here. And so that's it. So that's the quick intro to the basics of orbits, and I hope you guys have enjoyed that. Have a good day.